finding a volume, what we're doing is we're adding up a bunch of areas. Like with the disk method, we were adding a bunch of circles up to make a volume. With the washer method, we had one circle minus the other circle and added up all of those washers to get a volume. What we're going to do now is we're going to make paper-thin cylinders. So imagine here's a cylinder, imagine like a soup can, it has a label on it. Pulling off that label gives you a tiny piece of paper that has a tiny thickness. We think of that tiny thickness as our dx, because we want our dx to be as small as possible. That's what calculus does. If I took the piece of paper off of the soup can, it would make a rectangle with the circumference being the length and the height here. Now, in a function, and we're going to look at a picture here as one of the ones that we're going to be doing. So a couple examples later, I want to take this part right here, replicate it over here. Ooh, check out this. There we go. Replicate it over there exactly, and rotate this around the y-axis. So this point here to this point would make an open circle, this point to this point. All right. I'm going to take some moment here to try to visualize this. Can you see if you took the blue part? I know, I said we're looking at the picture first to get an idea of what this looks like and how we could use the cylinders to figure this out as opposed to using discs and washers. Okay? So, can you imagine this blue part, its area filled in, and then I take it like this and rotate it around the Y, creating this dish with an open part in the middle. Part in the middle would be open, the rest would be solid, wrapped around. This is part of what calculus is getting you to learn in this unit, is being able to visualize things in 3 dimensions when you're just given an explanation or a 2-dimensional drawing. If I wanted to do this with the disc method and the washer method, I would have to break it up into 2 parts. I would have to split it right here and do, if I cut this part, I would create washers. And then I would split it here again and do a second set of washers. I would have to do washers in 2 sections. Okay? With the cylinder, what we're doing here is we are taking one cylinder in purple. Here's the cylinder. I'll redraw the cylinder that was here. And we're imagining starting with a tiny cylinder here. And as we go all the way from 0 to 3, we add up all of those cylinders, and all of those cylinders together would make this full volume. That's the idea of the cylinder method. What's nice about the cylinder method is we don't have to stop halfway and do it twice. We can just do it all at once. So going back to our first slide, this is what one cylinder looks like. And the volume of one cylinder is just the circumference, which is 2 pi times the radius. And the radius, if you're going around the y-axis, always happens to be whatever your x-coordinate is. The x-coordinate becomes your radius. Your height of your cylinder is following your function. So your height is your y value of your function. That's why it's f of x. And if we add up all of these cylinders by doing the integral from a to b, we will get the volume of all of those shells put together, which gives us the volume of the shape. So here's some tips on drawing that. So you draw your radius perpendicular to the axis of the rotation, drop your height to the point, and then you have your cylinder. So let's look at our first example here. We're going to get rid of the red. Get rid of the red lines because they were for the washer method. So if we take any point along the blue, we can make a cylinder. The radius would be x. The height would be f of x, which is 3x minus x squared. And we remember, I always remember circumference times height. You can even write it out like that if you like. And then remember, I could pull out the 2 pi in front, because that's a number. My radius is my x value, so I can plug in x. My height is my y value, which in this case is 3x minus x squared. And since we're going from 0 to 3, our x values are changing, and we have dx. And once the setup is there, the rest is generally easy. You can multiply things out, do your regular integrals, and you could figure out your volume. Hey, no picture is drawn. So let's see if we can draw the picture first. My graph is x squared plus 2x. We want it bounded by that graph, the x-axis, the line x equals 1, and we're rotating it around the y-axis. So first of all, if I was graphing x squared plus 2x, I might find my two x-intercepts by factoring out an x. I'd get minus 2 and 2, and I would draw my parabola in blue, opening up, looking like this. We are taking the region bounded by that graph, the line x equals 1, and the x-axis. So the part that we are going to, that is bounded, is this section in green. That section in green is going to get rotated 360 degrees about the y-axis. I can even, if I wanted to, I can label this point when x is 1, y is 3, just so we can visualize it even more. And so if I was rotating this and drawing it completely, I would replicate this on the other side. I replicated that green part on the other side. Take these top points, make an oval, take these bottom points, make an oval, and I would imagine this green part rotated all the way around, which would create when I color that all in, there'd be, this whole thing would be solid. It would be open and a hole in the middle. So we could think of this as washers, with the outer radius always being 1. That's not hard. The inner radius would be the y value of x squared plus 2x. But just like in the video, what makes that a little bit difficult is it's hard to solve for x. You could use completing the square. It's not the end of the world. You could solve for x. And so the washer method wouldn't use anything outside of the math you've already learned. We could still use the washer method here. However, it's going to be easier if we take a cross section and we think about making a cylinder with that cross section. My radius is going to be x. My height of my cylinder is x squared plus 2x, and I'm just adding up all of those cylinders starting from 0 and going up to 1. Again, easier than the washer method, right? In the washer method, do you want to see how you'd have to do the washer method? The washer method in this example, you have y equals x squared plus 2x. You would have to think about wanting to complete the square, which would mean you'd add 1 in there and subtract 1. Or technically you could add 1 to both sides. You would have to square root and in the end you would get -1 plus or minus the square root of y plus 1, and you would have to decide which one do you have. Do you have the positive one, or do you have the negative one? Right? And so in this case, we would have the positive one. And that would be your inner radius. Your outer radius would be +1. And with your inner radius, you would then have to square it, and you'd have lots of square roots to deal with. I hope that you see in this situation, the cylindrical method is better. So they could ask this question on the exam, even though the cylindrical method is not formally part of the curriculum, and they won't ask direct questions in multiple choice that ask that. In this situation, it is way easier to find the volume with that. So if this were a long answer, and you used this method, they would give you full marks for that. And that's sort of the idea of mathematics all the way through. If there's an easier way, we should use that. That's sort of the pursuit of mathematics all through history has been, can I find an easier way to do this than what we've done before? Not that the old way is bad, but if there's an easier way, why not do that? So find the volume of the solid generated by revolving the region bounded by the graph of x squared, 12 minus x, to the right of x equals 1 and the y-axis. So again, we draw our x squared. We draw the line 12 minus x. They happen to intersect at 3, 9. we draw the line x equals 1. To the right of x equals 1, the only part that is bounded by all of them is this section right here. I'm going to take that section. See if I can do this. Take that section. I'm going to flip it over this way and redraw it. Draw a little circle there. I'm going to draw a little circle there. And one here.
I draw that shape right there.
That is the end volume that you would get. I'm going to color in my end volume. That's a crazy looking shape. So there's the work, just finding out where they intersected at that 3, 9. It's pretty simple algebra at this point in your math careers. And can you see that we could have a whole bunch of cylinders create this shape? But this time, the height of our cylinders is the difference between the top function and the bottom function. So my height of my cylinder, the top one, which is the 12 minus x, minus, sometimes when it's just adding brackets there makes you realize what we did. Each cylinder that's drawn, the height of the cylinder is the top function minus the bottom function. And again, what's nice in this cylinder method is when we multiply that out, none of the integrals are hard. They're just your regular power rule. And the rest is just simple algebra and adding and subtracting. And of course, if we can do cylinders around the y-axis, we can do cylinders around the x-axis. But now your radius is going to be your y value, and your height is going to be g of y instead of f of x. This is exactly the same idea, just switching your variables from x's to y's.
Why is it dx and not
Yeah. Why is it dx and not dy? Good question. Thank you. It is dy. There's a crazy looking function. 3y cubed minus y to the 4. So first of all, we're given the picture there, which is helpful, but if this question was just written as the region in the first quadrant bounded by the graph of the equation x equals 3y cubed minus y to the 4, and the y-axis is revolved about the x-axis, set up the integral and find the volume of the resulting solid, well, you could set x equal to 0 to find out where your y-intercepts are, and you would get y equals 0 and y equals 3. Now, we were given the graph in our notes, so you could see that from your graph. But now, we're taking this part right here. I'm going to color in green. We're taking this area.
What is that number right there? Looks like a hybrid. 2 and 3.
This one?
No.
There we go. Okay, to help you visualize it, I recopy that same shape. Well, my coloring wasn't as nice on this one. I recopied that same shape and drew it below. We've got one cylinder already there. If I wanted to draw the final shape, I could take these 2 points and draw an oval. I could take these points and draw an oval. I could color in the outside. And we get our dog dish kind of shape again. That's the volume that we want to find. Okay? So, why are cylinders nice? Well, we can take our cylinders all the way here. Our radius of our cylinder, again, I'll draw that cylinder in darker here. The radius of that cylinder is just your y value. The height of your cylinder, because it's turned on its side, is going to be your x value, and your x value is equal to 3y cubed minus y to the 4. So when we set up our integral, we're going from 0 to 3 of y times 3y to the 4, 3y cubed minus y to the 4. Yeah.
This is an off-topic question, but how many weeks do you expect to have to read for the exam?
Well, the exam is when? May 16th?
Yeah, it was like after.
We got a month,
Yeah.
right? You're free to start reviewing for your exam already. You can have all
Like
4
2 months
weeks.
ago, like a month ago.
It's a month to go.
I actually wanted to start a month ago.
No, I said I would start spring. Actually, I put in my notes. I'm not sure I have my notes for you, but.
The nice thing is some of the early units, we've been using them so much all the way through. It's sort of like, do you really have to restudy derivatives? No. Some of the early units we haven't been doing, like the definition of the derivative, the limits, those will be things you're going to have to look at again.
I don't even know what a limit is.
Curve sketching seemed to be a more challenging unit for lots of people, so that one we'll have to, and curve sketching is a favorite topic of the long answer of the exam. They like to give you a graph of the derivative, and you have to tell things about the original graph, its concavity, and all sorts of things. So we'll be looking at that as well. I mean, how many pages do we have left in our notes here? Not too many.
That's next time. Oh, my sister's
Okay.
next week.
Should we do one more example or should we be done?